Chris Brace, and this is the 6 o'clock news. Our top story today. A research group at the University of Warwick have found breakthrough new corkscrew-type structures, which they believe can target infections like MRSA and E. coli. MRSA is believed to have been the cause of 4% of all healthcare-associated infections. MRSA is a growing problem up and down the country due to having developed resistance to normal antibiotics. Currently, MRSA is treated with strong antibiotics, which have negative side effects for patients. So this exciting research could target the superbug, but with much less of their side effects. Over to our news correspondent, Rose Sutherland.
Thanks, Chris. And I'm here with scientist James Foster.
Good evening.
All right. He's going to tell us more about the issue. So, James, what's so new about these new molecules?
Well, Rosa, if you're asking, these molecules are actually not that different from a type of molecule which had been previously worked on before, called helicates, which was kind of investigated in the mid-20th century. Helicates are structures in which a carbon backbone kind of wraps around 2 or more metal ions in kind of like a corkscrew shape. And this corkscrew can either twist clockwise or anti-clockwise. And so the main difference is between these new Flexicates, for example, and the old helicates, is that simply that helicates are made in a mixture of clockwise and anti-clockwise, the anti-clockwise forms, while these new molecules can be made purely in one form. Scientists have found a way of making these structures from building blocks, which have their twist predetermined, if you will. And they link them together in such a way that a specific corkscrew will form.
Oh, I see. So what's the main difference between these clockwise and anti-clockwise forms?
Well, the twist, really, is what chemists call chirality. And to be chiral, a molecule lacks an internal plane of symmetry, meaning it cannot be superimposed on its mirror image.
So that's a bit of a complicated idea, James. Could you explain that to me in a more simplified way?
Yeah, the typical example that people often give are using your hands. If you look at your hands, you'll notice that they're actually mirror images of each other. And if you try and twist them in any arrangement, you'll actually find that they aren't superimposable on each other. And these corkscrew molecules, the Flexicates, are exactly like that. Because they're not superimposable, they have a lot of chemical properties that are the same, because obviously your hands are still the same. But because they're not superimposable, they react differently in your bodies and your biological systems.
There was a famous case of that, wasn't there, in the 60s, I think?
Yeah, you're absolutely right. There was a famous case, a compound called thalidomide in the 60s, where there obviously both the mirror images of the chemical was made, and both versions were given to the patients. And obviously, when the pharmaceutical companies came up with this drug, they obviously they only considered the one mirror image, because at the time it wasn't this idea wasn't fully understood. So yeah, they were looking for only the one mirror image, but in the end both images were given to the patient, and they discovered later on that one of the mirror images, the one that they didn't realize existed, actually caused birth defects. And even though the other version was effective as a drug, and this is typically the case, that the mirror images react in different ways. So one of the Flexicates, for example, could react in a negative way, and obviously won't target the bacteria of DNA that we want it to.
What do these drugs mean for the future?
Well, currently, the most active iron Flexicate molecules that have been synthesized have only been tested on non-mammalian cells, as in, to put it simply, it hasn't been tested on humans, for example. And it shows relative effectiveness against MRSA, but obviously, and low toxicity as well, which is really important. But obviously at the moment, it's still quite in its infancy. There's still a long way to go through all the trials and through all the rigorous steps that really, obviously, we don't want anything happening to people. But it is hoped that in the future it could undergo testing with humans, obviously. And it's gone through, obviously, the important first stage of showing promise. And it could be such a good cure, hopefully, in the future against MRSA. And it really does open up a whole another window of targeting bacterial DNA, and this could be extended even further against other kind of DNA. Maybe you never know, against maybe like cancer, and these helicate molecules that obviously Flexicates are based have practical uses in industrial use, such as catalysts, or as in materials as well. So this kind of chemistry is really exciting.
So what James is saying is, in the future, maybe this molecule could actually kill MRSA. For the viewers at home, we've got a very simplified representation of this. So I'm here at the University of Warwick with some genuine students. So what's your opinion on this new research?
Oh, I think wasting time on a condition that only affects about 4% of people isn't the best idea. There's maybe more pressing issues.
Yeah, I think this research is, it's really exciting, but it is still in its early stages, so we'll see how it goes.
Thanks, Rosa. Of course, this research is still in its early stages, but has a lot of promising possibilities, not only in the medicinal field, but also in materials and catalysts. And in other news, Cambridge football team today ended its 826-minute goal drought with a fine team performance. Here's the captain. Thanks, Rosa. Of course, this research is still in its early stages, but it has a lot of promising possibilities, not only in the medicinal field, but also catalysts and materials.
Oh.
Thanks, Rosa. Of course, this research is still in its early stages, but it has a lot of promising possibilities, not only in the medicinal field, but also catalysts, materials, and materials. Thanks, Rosa. Of course, this research is still in its early stages. It has a lot of promising possibilities, not only in the medicinal.
Take a breather.
Calm down.
Do you want me to type it up?
But no, it's fine.
You can do it.
You actually, it's not bad.
Chemistry between us.
Okay. That would be funnier.
Good one.
Yeah. If you wanted to something that I do it more like subtly.
The cameras.
Okay.
So is James going to be in
I
this?
don't mean to be bitchy, but we just...
Is James going to be in this?
It's going to get
Didn't we just
busy
do it?
very
I thought we just
soon.
did it.
No, I've got a little bit more to do.
Oh.
So James, are you?
Then you can talk.
What is it? Can you tell me so I feel comfortable what's going on?
It's nothing to do with you. You just sit there.
You just sit there.
It's not like I'm looking at the camera.
Okay, go, go.
Yeah?
You zoom in a bit on them.
Zoom in, right, you zoom in.
Do you want someone to cast it on?
Easy right now.
Yeah, probably.
Right, no. Okay, we're going now.
I'll phase it.
Oh wait, are we recording? Sorry, we are recording.
That's fine, dude.
Ryan has just recorded the last 2.5 minutes of what was.
Right, are we ready?